Now let's check what happens with the work with a spring. Now here we have an animation. I want you to pay attention. This green line is the equilibrium point, is where the displacement is 0, so it's very close to that. And with this pole, I am going to stretch or to compress the spring. Now you are going to see what happens to the displacement and the force while it's moving, but also with the potential energy. So look that when the string is being stretched, increases the displacement, the force, but also the kinetic energy. When it comes back to the equilibrium point, the potential energy is 0, and when it is compressing, the potential energy is increasing too. And in all time, the relationship is linear. So, because of that relation, we can calculate also the work done by a spring by calculating the area under the curve in a graph where we have in the x-axis the extension or the displacement of the spring and the force. Now remember, because of the Hooke's law, the force in a spring equals the constant of the spring times the displacement, and this is negative because remember that the displacement is always in the opposite direction of the force. So that's why we have this term here, the constant times the displacement for the force of the spring, and then the stretching or the compressing of the spring here. At any case, we are going to calculate the work done by that string by calculating the area, okay? And remember that the area of a triangle is base times height over 2, okay? So if we substitute this formula area, we know that base is x, in this case x1. The height is kx12, kx1, and divided by 2. If we simplify, we're going to have that. We have the constant, and we have the displacement squared over 2. And this formula, we saw it in the elastic potential energy. Let's do another example. Now we have a mass of 8.4 kilograms rest on the top of a vertical spring whose base is attached to the floor. The spring compresses by 5.2 centimeters. And then we have to calculate the spring constant of the spring and determine the energy stored in the spring. So a sketch of the situation should be something like this. So this is the floor and the spring is here, and then the mass is in this way. So the mass is compressing the spring. Now what data we have that mass equals 8.4 kilograms and the compression distance is 5.2 centimeters. Okay, then what we want to calculate is the constant of the spring and the energy stored in the spring, which is the elastic potential energy. So we're going to start. Okay, we have to consider the Hooke's law that states that the force of a spring equals the constant of the spring times its displacement. And remember, the negative sign is because the displacement and the force are in opposite directions. So I'm going to isolate K, but look, because of the mass is over the spring, the force that the mass is exerting is its weight. So weight is, we know, that is mass times the acceleration due to gravity, and that weight is a force. So I'm going to write here mass times gravity over the displacement. So the constant is going to be 8.4 kilograms times 9.81 divided by 5.2 times 10 to the minus 2. If I make the calculations, I am going to get that the answer is 1,585 newtons per meter. Now let's consider that we have two significant figures and two significant figures. So rounding my answer, I am going to have the value for the constant of the spring. Now let's calculate the energy stored in the spring. The energy stored in the spring is going to be the elastic potential energy, and the formula is 1/2 of the constant of the spring times the displacement squared. So now we have the constant of the spring, so this is going to be 1/2 times 1600 times the displacement, which is 5.2 times 10 to the minus 2 squared. Don't forget the square. Making the calculations and considering the significant figures, again we have two significant figures and two significant figures. The rounded answer is going to be 2.0 joules. The other answer is this one.